Okay, so just recall, however, that K bar E has dimensions, number of spatial dimensions times number of nodes in an element minus ND, which is the number of degrees of freedom with Dirichlet conditions on it, right? This times NSD times NNE. Okay? This is no different from before, except for the fact that now NSD is 2. That's all, right? Otherwise, it's exactly the same thing. Okay? All right, and then assembly is what lets us say that assembly over E of K bar E equals K bar, right? And this assembly process is just like we did in 3D. Again, nothing different, right? We just look at every global degree of freedom, look at every local degree of freedom from any element that has the same global degree of freedom and add up contributions in the matrix, right? And the same way for our other, for our vectors. F bar internal E, right? The assembly of all of these gives us an F bar. This assembly process is no different, right? Just look at global degrees of freedom that correspond to local degrees of freedom in every single element that they belong to, right? And just add up the contributions. Right? And in doing this, we may choose to say that E here runs only over the set of degrees of freedom that, it just runs, we need to only run over the elements that have a boundary coinciding with the Neumann boundary, okay? Okay, I just realized that what I did here for the dimensions of K bar E actually apply to K bar. This is corresponding to K bar. Okay. All right, so we observe that K bar is a rectangular matrix. It's not square, and we know why it's not square, because there are fewer degrees of freedom corresponding to the trial solution vector. Okay, so that last bit is exactly the same. So if you look at K bar, what we will see is that right, in general, it has fewer rows than columns, right? These are number of spatial dimensions times NNE, right? Whereas these are number of spatial dimensions times NNE minus ND, right, as we observed above up there. Okay, now some of these are some of these degrees of freedom that are in the D bar vector are known, right? Okay, we'd observed that fact before. Maybe some of these degrees of freedom are known, right? And what we do then is go back here and essentially eliminate the corresponding columns, right? So for instance, if this were A bar and that were B bar, right? This column would be the A bar column here, right? And then you would get the B bar column. Right? And corresponding to it, what we would see is that dA bar would be known and dB bar would also be known, right? The D bar, A bar, D bar, B bar, those degrees of freedom would be known. We just move them over to the right-hand side because they're known degrees of freedom, right? So that is known, right? And likewise, that one would be known. And why would it be known? That's right, because it corresponds to a Dirichlet boundary condition. Right, likewise this one. DIR for short for Dirichlet. Okay, right, and this column is what I've been calling before K bar, A bar, and this would be K bar, B bar. I should be using that as a superscript. Okay, and just as before, we move this all to the right-hand side. Okay, so what this gives us then is the full C vector here, now multiplying K and D, where K properly now has dimensions of number of spatial dimensions times number of nodes in the element minus ND square, right? And therefore C transpose and D are also of the same dimension, right? NSD times NNE minus ND. This is equal to C transpose F internal plus Fj minus dA bar, right? Just that degree of freedom, just that scalar, multiplying the K bar A bar column minus dB bar, multiplying the K bar B bar column. Okay, and this finally is our full F vector, also with dimensions NSD times NNE minus ND. Okay, and this has to hold for all C belonging to that same, to space of the same dimension. Right, and what that implies again is that KD equals F. Okay. All right, so as you see, there's really nothing to do here. It was just a matter of observing that our spatial dimensions run over 1 and 2, just recalling for ourselves how we would construct the relevant gradient fields using our basis functions. Observe that it doesn't matter whether we're working with quadrilaterals or triangles. There's something special in the case of linear triangles, which is that the Jacobian of the mapping is a constant. But other than that, it's all completely standard, especially once we form the elemental matrices and vectors. And in fact, the process of forming the elemental matrices and vectors itself is exactly as we'd followed in 3D. And then final global assembly also follows the same process, including the treatment of Dirichlet boundary conditions. Okay, so we'll end this segment, in fact, this treatment of two-dimensional problems here.